Okay, now we've looked at the sex-linked varieties. What I want to do now is talk a little bit about how some of those varieties can be made up. So for example, I've put on here, sometimes it takes two. What I mean by that is if we take the INO gene, so this is the gene that produces, or basically what it does is it, in the mutated form, it will remove, or it appears to remove, all of the colour except the ground colour of the bird. So in a green series bird, it will remove, the bird will look all yellow, and in a blue series bird, the bird will look completely white. In both cases they will have pink eyes because it's of the way the mutation works, but green completely yellow, blue completely white. And I want you to remember that, because let's have a look at the difference between those two birds in terms of the number of genes that are involved to produce those two different types of birds. So we'll flick back over now and have a look and do it via the Punnett square, because it's slightly easier to understand when you can see it laid out. So here are two Punnett squares representing two different crosses, and we'll start off looking at the top one of these Punnett squares where we've got a green split INO cockbird, and we've also got a green a normal green hen. So if we have a look at these two birds, the genes we're interested in then are obviously the blue gene and also the INO gene. So you'll remember from the previous video where we looked at multiple genes, predicting multiple genes, we will need to consider both of those genes. So along the top for the cockbird, we've got the X non-mutated INO allele and the non-mutated blue allele, and then we've also got the mutated INO allele and the non-mutated blue allele, and for the green hen we've got the non-mutated INO allele and the the non-mutated blue allele, and then we've got the Y chromosome and the non-mutated blue allele. And if we look at, these are the predicted outcomes for this bird. So we can now see that this one here is going to be a normal green cockbird. Contains two of the X chromosomes, so it's going to be a cockbird, no mutated of the INO and two of the non-mutated blue allele. So, and then this one here, once again, two X chromosomes, so it's a cockbird. It contains one of the mutated INO allele and both of the non-mutated blue allele, so that's going to be a green split INO cockbird. Down here we've got both of these two bottom row contain a Y chromosome, so they're both going to be hens. This first one here is going to be, we've got the on the X chromosome we've got the non-mutated INO allele plus a non-mutated blue allele, and then we've got the Y chromosome and a non-mutated blue allele, so that's going to be a normal green. Over here, however, you will see that we've got on the X chromosome the mutated recessive INO allele plus the non-mutated blue, and then we've got the Y chromosome and the non-mutated blue. So this one here is going to be a green series INO, which makes it a yellow bird. We said that the green series INO is all yellow. It's going to be a hen, and we refer to that as a lutino. So there's going to be a lutino hen. So that's that first one there, and notice that to get this, in effect, we just needed the INO gene alone to get the INO mutation alone to get the lutino. let's consider the next one down then. Okay, for this one it's slightly more complicated. For the cockbird we've got a blue split ino, and once again we only need to consider the blue allele and the blue gene and the ino gene. Because the cockbird's an all blue, we know it must contain two of the recessive BL1 genes. That's what we're going to call it there. So BL1 allele, sorry. So it contains two of the recessive blue allele, mutated blue allele. So we only need to consider that once because that's all it can pass on. But for its out on its X chromosome, it can pass on either the non-mutated ino allele or the mutated ino allele. So it can pass on one of those. So there's two options there, and we've put those two options in the two squares below. For the lutino, so we said that was a yellow or an all yellow bird. So the lutino split for blue, we've got, in this case, we've got the 4 to consider because it can pass on the X chromosome. It can only pass on the ino gene because it must contain the ino gene, the mutated ino gene on the X chromosome, but it can pass that on. But it can also either pass on along with that either the non-mutated blue allele or the mutated blue allele because it's split for blue, and on the Y, and the same for the Y, so it can pass on the Y chromosome and the non-mutated blue allele or the mutated blue allele, because once again it's, as we say, it's split for blue. So let's have a look at the possible outcomes here. So this bird here contains 2 X chromosomes, so it's going to be a cockbird. One of those X chromosomes contains the mutated ino allele, so it's going, but in terms of the blue gene, it contains one of the mutated blue allele. So this bird is going to be a cockbird, and it's going to be a green split blue split ino. So it's going to be a green split blue split ino cockbird. The next one across, we can see again that this cockbird is going to be split for blue, but it contains 2 of the mutated recessive ino genes. So we know that it's going to be an ino of some sort. It only contains 1 of the recessive blue allele, so it's going to be, once again, this one's going to be a green series bird, but because it contains 2 of the inos, it's going to be a yellow bird, so it's going to be a lutino split for blue. So this is a lutino cockbird split for blue. The next one down, this one here, once again is a cockbird, and that one's going to be a normal blue split ino. The next one across, once again, is a normal blue cockbird, but this one is going to be, if you have a look, it contains 2 of the recessive ino genes, so that's going to be a white series bird, so a blue series bird, sorry, so it's going to be an albino. And then the 2 below it, we can see that this bird here is going to be, it's going to be a green bird because it does contain 1 of the non-mutated blue genes, so it's going to be a green, normal green split for blue. This one here is going to be a lutino split for blue. This one here is going to be a normal green, again split for blue, and this one here is going to be a albino because it contains 2 of the recessive blue genes or mutated blue genes, and it contains the mutated ino gene. So as I say, what this shows us is that there is no albino gene. So sometimes you'll hear people talk about an albino gene. There is no albino gene. To produce an albino, you need two recessive varieties. You need the recessive ino allele, and you need the recessive blue allele, both in the same bird. This is why it's more difficult to make progress with an albino than it is with a lutino, because lutino contains one of the dominant varieties. So there we are. That's why sometimes it takes two, and this is true of a whole load of varieties. You know, the if you had a double factor white spangle, once again you need the spangle mutation and you need the recessive blue mutation on the same bird. So that's why sometimes it takes two. Right, what I'll want to do now is to talk very briefly about one of the conundrums in all of this, and that is the cinnamon opaline, or the opaline cinnamon bird. And what we'll do is we'll do some predictions using the looking at the opaline, which is also one of the sex-linked genes, and a cinnamon bird. So we're going to have an opaline bird and a cinnamon bird, and see if we can produce an opaline cinnamon. So here's the punnet square for our cinnamon cockbird and our opaline hen. Notice this time that we are considering both the cinnamon and the opaline genes, and therefore we need to represent that in both birds. However, both of these genes sit on the X chromosome, so we need to link them to the X chromosome that they sit on, and we do this by the dash. So you can see here for the cinnamon cockbird, we have two X chromosomes, which makes it the cockbird, and they both contain the same allele. So we've got a X chromosome that contains one of the mutated cinnamon allele and one of the non-mutated opaline allele, and then the same with the other X chromosome. For the hen, we've only got one X chromosome, so we only need to worry about that one, and the Y chromosome, which makes it the hen. And the X chromosome contains one of the non-mutated cinnamon chromosomes and one of the mutated opaline chromosomes, so one of the recessive opaline chromosomes, which is why the hen is an opaline. Notice the hen is not split for cinnamon at all, and notice that the cinnamon cockbird is not split for opaline at all. Okay, so we just need to make sure we're aware of that. Now, so we now bring this down together and compare it with these two across together. So in this first square we will have the X cinnamon dash non-mutated opaline and an X cinnamon dash mutated opaline chromosome. So both of those two will be on the same chromosome. So this bird here will be a cockbird, and it will be split for both opaline and cinnamon, but the splits will be on different chromosomes. Okay, so that's the split cinnamon is on that chromosome there, and that split opaline is on that chromosome there. And this one is exactly the same. So this bird here will also be a cockbird that is split cinnamon and split opaline, but with the splits being on different chromosomes. Let's have a look at the hen now then. So the hen will contain the X chromosome, which is cinnamon, from the cockbird, and it will contain a Y from the hen, the Y chromosome from the hen. So that bird there, so the hen will be cinnamon, and exactly the same here. It will contain the cinnamon. So from this pairing, from this cinnamon cockbird with an opaline hen, we can only get, from looking at this pairing, we can only get cinnamon hens and normal cockbirds that are going to be split for opaline and cinnamon. So from that pairing we get no opaline cinnamons, and indeed if we paired one of the offspring back to one of the young, there would be no difference, so we would still not get any opaline cinnamons. In fact, let's try that now. So here we are, we've set up this punnet square here for this offspring and this offspring, and there are the various allele that we are concerned with. So let's have a look what we're going to get here. So we're going to get the X cinnamon dash opaline from the cockbird, and we're going to get the X cinnamon dash opaline from the hen. So we're going to get the mutated cinnamon gene from the cockbird and a mutated cinnamon gene from the hen, but neither of the opaline allele are the mutated time, so that's going to be a cinnamon cockbird. We're going to get an non-mutated cinnamon allele from the cockbird with a mutated opaline, but we're only going to get the non-mutated cinnamon from the hen and the mutated and the non-mutated opaline. So there we go, so the mutated cinnamon, non-mutated. So once again this bird here is going to be a normal split opaline, split cinnamon, because it contains only one allele for the recessive opaline and only one allele for the recessive cinnamon. If we have a look at this bird here, it's going to contain the mutated cinnamon gene from the cockbird and a non-mutated allele also from the cockbird, and for the hen it's going to inherit the Y, so that's going to be cinnamon hens, and over here it's going to get the non-mutated cinnamon allele from this chromosome here with the mutated opaline, and then from this it's going to inherit the Y chromosome from there. So it's going to be opaline hens. So from this pairing we're going to get cinnamon cockbirds, cinnamon hens and opaline hens, but we're going to get, once again, we're going to get no opaline cinnamons. And when you look at this, when you do this, no matter how you do it, no matter how many different types of pairings you get, if the opaline and cinnamon allele or mutated alleles sit on different X chromosomes within the cockbird, you will never get opaline cinnamons in the hen. It's just not possible based on the prediction. However, I know, having breeding opaline and cinnamons, that even from this very initial pairing, this top pairing here, there is a possibility that I will get opaline cinnamons. So something's happening with these birds that is not predicted using the Punnett square. There's something strange going on, something unusual going on, that we don't predict an outcome from the Punnett square. And indeed we will look at that, how that is happening when we reconsider the linked allele, so chromosome linked allele in part 7 of this guide. We'll cover that in part 7, and we'll look at why we can get opaline cinnamons. So that's it for this particular video. I hope you enjoyed it. I hope you understood that. Like I say, there is more in-depth information on this, and probably a slightly more in-depth explanation of this in the guide. So do go across to the Shed Talk Facebook page. The guide is around there, so the PDF guide is there for you to read through, and so it covers everything that's in here and the future parts of this video guide. It's free to download, so just go across, join the Shed Talk Facebook page and download the guide if you want to do look at this in a little bit more depth. In the next video, so in part 6 of this guide, we're going to look at where a mutation, where an allele, so might mutate more than once. So where we will have more than one mutation sitting in the same locus, and how we predict the outcomes from that. But until then, like I say, I hope you enjoyed the video. Please do like, hit the subscribe button if you haven't already subscribed, and do feel free to comment.